Hello everyone. Today we will be talking about the emitter-follower transistor circuit. First, we'll provide an overview of the emitter-follower circuit, its uses and overall properties. Then we'll continue on by briefly going over a common biasing circuit for the emitter-follower, before moving on to the small signal model, solving for the circuit's three main parameters: voltage gain, input resistance, and output resistance. In Part 2, we'll go over a lab demonstration of the circuit and discuss an analysis technique called impedance reflection that can simplify the thought process of designing with emitter-follower circuits. The emitter-follower circuit, also called the common collector circuit, is a single transistor circuit that provides unity gain, that is, gain of 1, voltage buffering. In other words, a voltage source with a high output impedance can be input into the emitter-follower circuit, and the output will be low impedance. This is a very useful circuit because many circuits must be driven by sources that have relatively low output impedance, and many sensors or transducers have high output impedance. And so in order to have a sensor signal drive a circuit that requires a low impedance source, you need something to serve as a buffer between the sensor and the circuit to be driven. The emitter-follower circuit can provide this functionality. It's important to note, however, that this circuit does not provide voltage gain. In fact, it provides a slight amount of voltage loss. But that is usually not a big problem, especially if there is gain elsewhere in the signal chain to compensate for the follower loss. Here we have a schematic of the basic form of an emitter-follower circuit. We have an input voltage on the base with a source resistance, a resistor from the emitter to ground, and a supply voltage on the collector with the output taken from the emitter this time, not the collector. As before with the common emitter, in order to get this circuit actually biased properly so it can work, we're going to have to add a few more components. So here we've added two biasing resistors, an AC coupling capacitor on the input and an AC coupling capacitor on the output. There is no bypass capacitor on the emitter resistor, which is a notable difference from the biasing circuit we applied to the common emitter circuit in the previous video. Let's start by converting this to the biasing circuit at DC by opening up the capacitors. So here we have a very similar circuit to the biasing circuit from the common emitter, with the notable exception that there is no collector resistor. So, recalling the equation for collector current we derived in the previous video, we see that it is still valid since it had no dependency upon collector resistance, provided we ensure the transistor is in the forward active region. However, this time I'm going to add back in the effect of the base current on the base voltage, since it's best to keep that term in mind, since it is often large enough to be considered when using this kind of biasing circuit. I was a bit too quick to apply that approximation in the previous video. Recall that this portion of the equation is the approximate value of the base voltage VB, with this equation being the more accurate value, resulting in this modified equation. Now all we need to do is ensure the transistor is in the forward active region. Recalling the definition of forward active region, we see that it's easier to ensure this transistor remains in the forward active region because we simply make sure the VB is less than VCC, since the collector voltage VC equals VCC. So now that we have IC, we can move on to the small signal model for this circuit. So here we have the overall circuit again. And now, shorting the capacitors and converting static voltages to ground, we have the AC version of this circuit. So using the hybrid pi model, we convert this to its small signal equivalent circuit. The first thing we notice here is that the emitter is not grounded, which is much different than what we dealt with in the common emitter. Second, we'll note that the collector is grounded, which will weirdly make RO in parallel with RE, whereas before it was in parallel with RC. So we make that slight adjustment to the schematic to simplify it. Note that I call the current through this resistor combination IE prime instead of IE. The current IE prime is equal to GMVBE plus IB. This can be a bit confusing since I've called the collector current IC equal to GMVBE, whereas the true collector current is GMVBE plus the current through RO. However, since the currents are labeled on the schematic, you can observe them where they are in the circuit. Just be careful not to assume that one person's IC is the same as my IC, so to speak. Anyway, the next thing we're going to do is to split this circuit into two pieces at the base. We'll solve the right circuit with VB as our input voltage rather than Vin. This will simplify the circuit significantly, and once we have the gain and input impedance of that circuit, we can easily adjust it to incorporate the left circuit. So now we have to think about what we need in order to get the gain of this circuit, which in this case is Vout over VB. So we need to get Vout in terms of VB and known constants. We'll start with Vout and work backwards. The most obvious expression for Vout, using Ohm's law, is IE prime times the parallel combination of RE and RO. Now, IE prime is equal to IC plus IB, and recalling that IC is equal to beta IB, we see that IE prime is equal to beta plus 1 times IB. This allows us to convert the Vout expression into an expression containing only known constants and the unknown current IB. Now let's apply Kirchhoff's voltage law around the loop containing VB, R pi, and RE in parallel with RO. Substituting in our expression for IE prime, we're able to get an equation in terms of VB and IB and known constants. Rearranging this equation to get an expression for IB in terms of VB and known constants, we get this equation. And earlier, we derived an expression for Vout in terms of IB and known constants. So we can substitute in our new expression for IB into the Vout equation, which gets us this. Rewriting R pi in terms of beta and GM, so we have all the beta terms exposed, we now divide top and bottom by beta plus 1 to get this somewhat simplified expression. Seeing this beta over beta plus 1 in the denominator, we recall that this is the definition of the transistor parameter, alpha. And so this allows us to clean up the expression a bit more. So just taking the final step to divide both sides by VB, this is our gain of the circuit when the input is taken to be VB. So this looks like a kind of divider circuit between RE parallel RO and alpha over GM. Indeed, since GM is a conductance parameter and alpha is unitless, alpha over GM is a resistance parameter called RE. We'll talk more about RE in part 2. So let's pause for a moment and look at this equation. We said at the beginning of the video that this circuit is supposed to have a gain of around 1. But it doesn't look like a gain of 1, it looks like a resistive divider. Let's assign some reasonable values to these parameters to see what gain we get. So setting the collector bias current to 1 milliamp, beta to 100, the emitter resistor to 1 kiloohm, and the early voltage to 100 volts, we get a resulting value for alpha over GM of about 25.74 ohms, and for RE parallel RO we get about 990.1 ohms. This results in a gain of about 0.97466. And we can see that increasing RE and increasing IC would generally push this closer to 1. So as expected, this is a gain of close to 1, but not exactly 1. So now that we've got this expression for gain, let's get an expression for the input impedance. For this circuit, input impedance is defined as VB over IB. We already derived an expression for IB in terms of VB earlier, so using that, we can rearrange it so that we have an expression for Rin. Here we see that the input impedance is much higher than the input impedance of the common emitter circuit by beta plus 1 times RE parallel RO. Note that the output load of the circuit would also affect the input impedance as it would be in parallel with RE and RO. Okay, now that we have the gain and input impedance of this circuit, we can add back in our source resistance and biasing resistors. The effect of the source resistance and the biasing resistors is to apply a resistive divider to the input voltage. This resistive divider, however, incorporates the input resistance of the right half circuit we just derived. So to get gain, we first want to get VB in terms of Vin, which is just this resistive divider, with the biasing resistors in parallel with the input resistance, with respect to ground, looking into the base, which we previously calculated. Next we expand that equation out, and noting that Vout is equal to the gain from the base to Vout times the base voltage, we can compute Vout by substituting in the expression for VB in terms of Vin above, in for VB, and substituting in our expression for AVB we calculated previously, which can be easily converted to the overall gain of the circuit, AV, by dividing both sides by V in. So this monstrous equation is our gain equation when incorporating the biasing resistors and the source resistance. Moving on to input impedance, we see that we've done the lion's share of the work already with the input impedance looking into the base. All we need to do is incorporate the biasing resistors which appear in parallel with R and B. And we unpack R and B for clarity. Note again that RS is not involved in this expression because RS is part of the input circuit and thus separate from the circuit's input resistance. We have one more parameter to derive before we take a closer look at these expressions: the output impedance. The output impedance calculation is a little more complicated. The method we'll use is to zero out the input voltage and apply a test current source Ix on the output and solve for the output voltage Vout in terms of Ix, which will then divide by Ix to get the output impedance. This is sort of the long way to calculate the output impedance here, but it is using general techniques that apply to other circuits. We'll discuss some other methods of doing this analysis in part 2 of this video that can simplify the process, using impedance reflection. Let's start by aggregating the impedance on the base and the impedance on the emitter into the variables Rs' and Re' respectively to make the equations more compact. So we recognize that Ix is flowing into a current divider between Re' and the impedance looking into the emitter. So let's define that unknown impedance as Rout' such that our desired parameter, Rout, is equal to Rout' in parallel with Re'. Using the current divider equation, we know that negative IE' is equal to this expression. It's negative because of the direction of IE' versus the direction of Ix. Noting the current IE' is equal to IC plus IB, and that IC is in turn equal to beta times IB, we can get an expression for IE' in terms of IB, then invert that equation so that we have an expression for IB in terms of IE'. Now that we have an expression for IB in terms of IE', we take a look at the circuit loop containing Vout, Rπ, and Rs' and apply Kirchhoff's voltage law to it. This allows us to construct an expression for Vout in terms of IB and known resistances. So, substituting in our expression for IB, we get this equation. Then we substitute in our expression for negative IE' we got from the current divider before, and now we have an expression for Ix in terms of Vout and known constants, except for Rout', which is still an unknown in there. So we divide both sides by Ix to get Rout on one side of the equation. Now we recall that Rout is equal to Rout' in parallel with Re', which we then substitute in for Rout in the equation above. Now we finally have one equation and one unknown. So with some simplifying, canceling out, and rearranging, we get an expression for Rout' in terms of known parameters. Now we can use our definition of Rout' to calculate Rout in terms of known parameters by substituting in our newly calculated expression for Rout' into this expression for Rout. So first we expand out the Rs' proxy variable. We could stop here, but we have both Rπ and beta in this expression, which can be further simplified by recalling that Rπ is equal to beta over Gm. And substituting in Rπ and separating out that term a bit, we recall that beta over beta plus 1 is a familiar term we previously defined as alpha, which for high beta is pretty close to 1. This gets us to our final expression for Rout. Now that we have the gain, input impedance, and output impedance, let's take a closer look at those parameters. So these equations have a lot of terms in them and seem a little overwhelming to parse. As in previous videos, we will make approximations to make the circuit easier to deal with. It's important to note that some of the conditions required for the approximations to be valid are not easy to adhere to and may be more trouble than they're worth. You can always fall back to the more accurate equations after using the approximate equations. Here are the rules we must adhere to for the approximations to be valid. First, if you use a biasing network like the one we've used here, you need to ensure the biasing resistors are very high, such that their parallel combination is much higher than Rπ plus beta plus 1 times Re parallel Ro. Second, we assume that Rb1 in parallel with Rb2 is also much larger than Rs. And third, we assume that Ro is much larger than Re. Applying these approximations to the gain equation, we can eliminate RO and the biasing resistors from all the parts of the gain equation, resulting in this expression. The input resistance reduces to just the third parallel term, and with RO removed. Then the output resistance reduces to a portion of the third term in parallel with RE. Now that these equations are a bit easier to deal with, let's take a closer look. With the gain, we notice that there are two resistive dividers cascaded together, meaning multiplied together. The one on the left is between the emitter resistance and alpha over GM, and the one on the right is between the source resistance and the input resistance. The one on the right makes intuitive sense. Effectively, any circuit that has an output impedance that goes into another circuit with an input impedance will have its voltage attenuated by the divider produced by those two impedances. The portion on the left is really a manifestation of the divider between R-pi and RE, except incorporating the effect of beta. Regarding the left divider, RE is usually much greater than the quantity alpha over GM. Regarding the right divider, oftentimes Rn and Rs are designed such that Rn is much larger than Rs. Under these two conditions, this equation approximates even further to approximately 1, which holds up pretty well for circuits that do not need precise gain. Looking at Rn, we see that it's a combination of R-pi and Re multiplied by beta plus 1. This is one reason why beta is important for this circuit. The greater beta is, the less of an effect Rs has on the gain, and the better it serves as a high input impedance buffer. Additionally, we should note that since Vout is taken off of the emitter, the load impedance of the circuit this is connected to will appear in parallel with Re, and thus affects the input impedance. So while you may be able to make Re large, oftentimes the load resistance is far more important here. This is an interesting contrast with the common emitter, as the load resistance of the common emitter had no effect on the input impedance in the low-frequency model. And finally, the output impedance. The output impedance is Re in parallel with this second term, dependent upon Rs and alpha over GM. First, let's think about when Rs is 0. If Rs is 0, then the output impedance becomes Re in parallel with alpha over GM. But Re is almost always much larger than alpha over GM. If it weren't, then the gain wouldn't be close to unity because of that left-hand side divider in the gain expression above. As a result, we can neglect Re, and the output impedance just becomes alpha over GM. This is the lowest output impedance we can get with this circuit. And it's worth noting at this point that given how low alpha over GM is at 1 milliamp collector current, about 26 ohms, you should bear in mind that there are internal resistances from the physical metal connections within BJT parts that will start to come into play. So don't assume you can just crush this impedance down to less than an ohm by dumping 100 milliamps of current into the collector. At some point, the physical resistance of the connections in the part are going to be the limiting factor. So, the lowest output impedance is alpha over GM. However, as we've said multiple times already, this is designed to be a circuit that takes a high input impedance and translates it to a low output impedance. The limits of that effect revolve around the quantity beta plus 1. Effectively, this circuit transforms Rs on the input into Rs over beta plus 1 on the output, plus a little bit extra from alpha over GM. If Rs gets too high, yes, Re will take over as the dominant term, but the gain will also drop due to the divider on the right-hand side of the gain equation. So if Rs is much larger than beta plus 1 Re, then we get the same problem. R-pi, as we've noted before, is equal to alpha over GM times beta plus 1. So we can actually convert this right half of the gain expression into this, which shows the divider after the beta plus 1 multiplication is applied, which is a more apples-to-apples comparison with our output impedance expression. We see that the divider is made up of the quantity Rs over beta plus 1 and the quantity alpha over GM plus Re. So while Rs can get high enough to the point that Rs over beta plus 1 is approximately equal to Re, and thus Re dominates the output resistance, at that point the gain will be dropping significantly. So, all in order for this to work as a good buffer, you need Rs to be much less than R-pi and a high enough bias current so that alpha over GM is low enough to be your desired output impedance. That concludes this video. In part 2, we'll do a demonstration of the emitter-follower circuit in the lab, and go over an analysis technique that helps with analyses involving emitter impedance called impedance reflection. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.